Last time we talked about how we obtain the standard electrode potentials for a metal by connecting it to the standard hydrogen electrode. We assume by definition that the hydrogen electrode contributes 0 volts to the overall potential difference. So whatever we get, the reading on the voltmeter is always the standard electrode potential for that metal. We then just have to be clear that the electrons can move in different directions depending on the reactivity of the metal. That's more or less reactive than hydrogen ions. So if we have a very reactive metal, the standard electrode potentials are always negative numbers. A less reactive metal, the standard electrode potentials are positive numbers, depending on the direction the electrons are moving through the voltmeter. And you'll get this experience yourself if you ever connect up a voltmeter and it's got a negative reading. Well, if you swap the wires around, it'll give a positive reading. It also gives us an appreciation of the tendency of a reaction or a half equation to happen. So remembering that positive E0 values are kind of the good values, they're the likely reactions to happen, we can say, well, copper ions like forming copper to the tune of 0.34 volts. Potassium ions definitely don't like forming potassium. It's a very hard reaction to make happen. It's very rare that we'd see potassium ions forming potassium metal in the lab. It's much easier to add a bit of potassium to water and away goes. Lots of lilac flames and sparks and fire, and potassium ions form very readily. And the reason for that is that the sort of downhill direction for potassium ions is potassium is moving towards ions, and potassium to K plus, so that reaction there would have a electrode potential of 2.92 volts. Okay, so we can use this to predict the voltage that would come from a cell. So if we go right back to the beginning of the very first thing I did, the demonstration was between zinc and copper. Well, if I look at the numbers here, I want to have an overall positive number for a cell. Yeah, cells always know which direction to go in. So the zinc is going to react and form zinc 2 plus to the tune of plus 0.76 of a volt there. And the copper ions are going to form copper to the tune of plus 0.34 volts there. If you missed my sleight of hand, let me just go over that again. I've got two reduction reactions here. I can't have two reduction half equations in a reaction. I've got to have a reduction and oxidation. If I swapped the direction of this reaction, it would be minus 0.34 and minus 0.76, which would give me a negative number overall. The only way the reaction is going to be possible is if zinc reacts to form zinc 2 plus and then copper 2 plus reacts to form copper. Because I've changed the direction of that reaction, I changed the sign of the E0 value, so it becomes plus 0.76. And when I add those together, we get an overall cell potential difference, sometimes written E0 just with the cell there. So these are our E0 values, 0.76 and 0.34. Everything's measured in volts. Okay, super duper. So let's do another example. What would I get if I added, well, let's add magnesium to silver. Let's really push the boat out. Okay. So first of all, look at the numbers. Clearly magnesium is the more reactive metal. Clearly I need to reverse the direction of this reaction. So magnesium needs to react and form magnesium 2 plus ions, and that would enable silver ions to pick up an electron and form silver. Magnesium to magnesium 2 plus would be plus 0.238 volts because I'm going in the opposite direction to the arrow, so I change the sign. Silver plus to silver, that's just the number it is, plus 0.8 volts. Just before we go on, is there anything at all that I need to think about before we add those numbers together? because the aware amongst you will have noticed that silver's only gaining 1 electron. Magnesium is giving away 2. And if there's anything I've drilled into you over the years of writing redox overall equations, or combining 2 redox equations together, half equations rather, we need to balance the electrons. So if this reaction was happening, I would have to have magnesium and 2 silvers reacting to make 1 magnesium and 2 silvers. That will be the overall reaction equation. So I've doubled the silver. Do I need to double the 0.8 volts? And the answer is a very, very simple no. No. Used as is. Why? Well, ask a physicist, but basically potential difference is not per mole. Voltage is not about quantity. The way I think about it is, if you have a river flowing down a hill, maybe it goes over a waterfall. The height of that waterfall is the potential difference between the top and the bottom. It's the amount of energy that the water will gain falling from the top to the bottom, in the same way that the electrons have energy because of the potential difference between the 2 electrode values. If there's less water going over the waterfall, that does not make the waterfall lower. The waterfall is always the same height. Less water, there's less water, it's less flow. So the water is kind of the per moles, but the potential difference is the height of the waterfall, which doesn't change. So voltage is not per mole. It's always 0.8 volts for silver, however much silver goes over the waterfall, and I don't have to change the values. Okay, it might seem strange after years and years of, well, not years and years of, a year of drilling in that if I'm doubling the equation, I have to double the delta H value, and that's still true, and the same for entropy and making delta S, but I don't have to do it for E naught. So what have I got here? I've got a sneeze, that's what I've got. Add those together. So plus 3.18 volts. Okay, fantastic. So we can use our list of electrode potential data to calculate the overall cell voltage given the 2 electrodes for that cell. But it doesn't stop there, because remember, the original situation was, what happens if I add a piece of zinc to copper? The zinc reacts, the copper gets formed, and so on. So what happens if I put a piece of zinc in copper sulfate? Will that react? Will that react? This is not a cell I'm making here. I'm again literally just putting a piece of zinc in some copper sulfate and sitting back and watching what happens. Does it react? Well, yes, it does, of course. But how do we know it reacts just from the electrode potential data? Well, we look it up. So zinc would be forming zinc 2+ ions. So we're going in the opposite direction for that reaction. So we change the sign of the electrode. And copper 2+ would be forming copper plus 0.34. Add those together, and the value is positive. Now, for a cell will always work out which way to go. A cell will look at the different electrode potentials and say, yeah, I need to go this direction. But if I'm doing a reaction, I've only got a piece of zinc and I've only got some copper sulfate solution, the reaction either happens or it doesn't. And the reaction does happen because the E naught value for that cell is positive, and we're back in the realm of delta G, aren't we? E naught for the cell is positive, the reaction is spontaneous. Okay, just to reinforce, we're talking about a reaction now, not a cell. So let's give another example. what happens if I don't know, drop a piece of silver in some copper sulfate? So then we'd look at that while I'm dropping silver in, so it would be silver to Ag plus. I'm reversing the direction of that electrode reaction, so I change the sign of that E0 value. And then copper 2 plus to copper plus 0.34. Add those together, and what do we get? Minus 0.46 of a volt. It's negative. And just like handling delta G, we'd say if E0 for the cell is negative, we could say the reaction is non-spontaneous, or we could say it's not feasible, or we could just spell it out. Reaction does not take place. If I put silver in copper 2 plus solution, nothing happens. Now that's very helpful because I've completely left that realm of cells. Cells, quite a specific little niche bit of chemistry. Well, maybe not so niche now, and we're all trying to drive around in electric vehicles, and we've got battery-based devices all over the place. But chemical reactions, we're talking about all chemical reactions now, come in many different forms, and we can now use E0 data to work out if a chemical reaction will take place. We will look at some examples of those in the next lesson.